Vanakkam. Welcome to this video on biomechanics. We have been looking at time dependent deviations in elastic behavior of biological materials, that is viscoelasticity. Specifically, we looked at a couple of models of viscoelasticity, namely the Maxwell model and the Voigt model. And we looked at creep and stress relaxation functions for these two models in the previous videos. Now, in this video, we will look at another model of viscoelasticity called as the Kelvin model. Okay. This is also called as the standard linear model. Okay. This is called as the standard linear model, and we will derive the creep and stress relaxation responses for the Kelvin model. Using the Kelvin model, we will derive the creep and stress relaxation responses. Okay. Now, what is the Kelvin model? The Kelvin model essentially incorporates both the Maxwell and the Voigt model, or it is a combination of Maxwell and Voigt model. So, there are two springs. One spring is the series spring, that is that spring. I am going to call this spring as the series spring. Throughout this lecture, I am going to call that spring as series spring, and it has the spring constant K1. And there is one more spring that is parallel to the dashpot that I am going to call as the parallel spring. This is parallel to the dashpot as in the Voigt model, and it is having a different spring constant K2. Its spring constant is not K1. Its spring constant is not K1, but rather K2. And you have the dashpot that is having one series spring and one parallel spring. The combination of these together gives rise to this Kelvin model or the standard linear model. Okay. So, let us remember spring constant, something that we need to remember throughout the lecture, is the spring constant of series spring K1 and the spring constant of the parallel spring is K2. Let us remember this K1 was called as K in Maxwell model. And this K2 was called as K in Voigt model. Okay. So, we are trying to relate the current Kelvin model with the Maxwell and Voigt model, which we already know. What was called as K in Maxwell model is now called K1. What was called as K in Voigt model is now called K2. And there are these two springs, one in series and one in parallel to the dashpot. Now, the length of the dashpot is that is x1 t. What is it? It is x1e plus x1. The length of the series spring is that, is it not, x2t. What is it? That is x2e plus x2. Okay. Now, what is the total length? The total length is some xt, and that is, what is it? That is x1t plus x2t. It turns out this total length is also the length of the parallel spring. Okay. This is also the length of the parallel spring. You need to remember this. I am going to call this equation as equation 1. Now, what is the force in the dash part and the series spring? I am going to call that force as sum Fa, force in dash part and series spring. This force is the same in both the dash part and the series spring, that I am going to call as Fa. Okay. What is the value of this Fa? I can write that. How do I know? Because I know the characteristic of the dash part and the spring, I can write the expression for Fa in terms of C and K1. I can write this. Okay. And remember, Fa is the same for both the dash part and the series spring. For the parallel spring it is different, but we will come to that in just a little bit. Okay. That is C dx1 by dt. Is it not? X1 is the dash part length. Is it not? C dx1 by dt. Remember dxe by dt is 0, regardless of whether that is for a spring or for a dash part. Dxe by dt is 0. That is why it is an equilibrium length. For the spring, the equilibrium length is assumed to not change. That is, its resting length for a given spring, the resting length is a constant regardless of the passage of time. So, if I differentiate that with respect to time, I will get 0. So, essentially this is dx1t by dt, but that is essentially dx1 by dt. Okay. This is dx1 by dt, and that is also k1 x2. Remember, x2 is the deformation, x2 is the deformation in the series spring, and its spring constant is k1. So, the force is k1 times x2. Please pause the video and check if you are understanding, or if what I am saying is clear. Okay. Check if this is correct. Okay. I am going to call this equation as equation 2. Okay. Now, what is the force in the parallel spring? Is that the same as the top combination? Is that the same as the combination of the dash part and the series spring? The answer is no, because it is the length that is the same, not the force. Is it not? So, that is some other force Fb, and what is it? That is dependent on the parallel spring constant K2 and the deformation x. Is it not? That is K2 x, not x2, K2 x, because that is the total length. Okay. Once again, take some time and check whether this is correct. For the top spring or for the series spring, the force is k1 x2, because it is deforming to x2 value, whereas the parallel spring deforms to the value x. So, the force developed in the parallel spring is k2 times x, not k2 times x2. Please note this, there is a difference, and this difference is very critical for the rest of the analysis. I hope this is clear. If it is not clear, I request you to again watch both the Maxwell video and the Voigt video, and check this video until this point. You will definitely understand. Okay. It is not k2 x2, but rather k2 x. and I am going to call this equation as equation 3. Okay. Now, what is the total force? The total force is the sum of the two forces Fa and Fb, and that is F is equal to Fa plus Fb. Now, it is somewhat confusing as to why are we doing this? What is our goal? What is our goal? What is our goal? Let us write it down. Many times it is very useful to write down your goals. When you write down your goals, you have made a commitment with yourself. It is like a contract that you have made with yourself. And because there are so many things that are happening, I would like to write down the goals of this derivation, not my life goals. What are my goals, or what is our goal in this exercise? To derive an expression involving f df by dt, x dx by dt, k1, k2, c. To derive a relationship between the forces and deformations involving only f df by dt, or f comma df by dt, x comma dx by dt, k1, k2 and c. This is all I want. I do not want to have other things in my expression. I want to have a relationship between force and the deformation. I want a relationship between f's and x's. I do not want in particular fa, fb, x1, x2. This is something that I do not want. Let us remember this. This is our goal. Okay. Now, let us take equation 2 and do some rearrangement. Okay. What it says is Fa is Cx1 dot. Remember what it says. It does not say Cx dot, but rather Cx1 dot. So, this implies x1 dot is Fa by C, right. What it also says is Fa is k1 x2. Now, if I differentiate this expression Fa is equal to k1 x2, or rather I can first write this as x2 is equal to Fa by k1. Now, if I differentiate this with respect to time, I will get x2 dot is Fa dot times 1 by k1. Let us, for clarity, let us write this in the expanded form as dx2 by dt is dfa by dt times 1 by k1. Is it not? We have derived this or something similar to this in a previous video. I hope this makes sense. I hope there is no confusion about this part. Now, let us reiterate our goals. What are our goals? Our goal is to have an expression between f and x involving only k1, k2, c df by dt and dx by dt, but not fa, fb, x1, x2. k1 and k2 are okay, but x1, x2, fa, fb are not okay. This is our goal, remember. This is our goal. Very, very critical to keep your goal in your mind as to why you are doing what you are doing. This is very, very critical. Okay. Always keep moving towards your goal. This is our goal. We may have to revisit this slide from time to time because we have to take this some of these equations to the next slide. Now, what is dx by dt? Because x is x1 plus x2, is it not? So, what is dx by dt? Dx by dt is dx1 by dt plus dx2 by dt, or x1 dot plus x2 dot. In the previous slide, we derived what is x1 dot and what is x2 dot. Let us write it up. Once again, let us remember let us note dxe by dt is 0 because equilibrium length does not change with time. All right. Now, let us go back and find out what is dx1 by dt and what is dx2 by dt and write it up. Okay. dx1 by dt is this, is it not? That is Fa by C. Let us write it up. That is Fa by C, and dx2 by dt, sorry, this is equal to, is it not, x2 dot is Fa dot times 1 by k1, which is equal to dx2 by dt, or which implies rather that is a line between them. Okay. dx2 by dt is dfa by dt times 1 by k1, that is dfa by dt times 1 by k1. Is this clear? I hope till now things are clear. If it is not clear, again I am requesting you to pause the video and check the flow of the math. So far I have been presenting this a little patiently so that you will be able to catch up. But if you are not, pause the video, go back and check, because this is a very critical topic, not just from your exam point of view, but also from your understanding point of view. For everything, this is a critical topic. Okay. So, do check this. Now, a question is, what is the relationship between the total force and Fa and Fb? What is the relationship between Fa and Fb? Because in this equation, it seems to me like I am only having Fa. What is the relationship between Fa, Fb and F? That is the question. Okay. Well, I know that. That is, Fa is F minus Fb. How am I saying this? Well, that is here, is it not? That is here. I am going to call this equation as 4. Okay. F is Fa plus Fb, that means Fa is F minus Fb. But what is Fb? We know what is Fb. Fb is that K2x. It is not K2x2, it is K2x. So, I can now write this as F minus K2x. Fa is F minus K2x. How do I know this? This is from equation 3 and 4. I have this equation. Okay. Fa is F minus K2x. Now, I can substitute for Fa in the above expression for dx by dt. Okay. I am going to call this as equation 5. Now, I can substitute for Fa in equation 5. Okay. What is it? But before that, let us try to find out what is dFa by dt, because here I have Fa, then what would be dFa by dt? That would be dF by dt minus K2 dx by dt. This is dFa by dt. I have Fa and I also have, because if I want to substitute for Fa, I also need to find out what is dFa by dt, because both Fa and dFa by dt are there in equation 5. I need to find Fa and I need to find dFa by dt to substitute in equation 5. Okay. I am going to call this as equation 6. Now, substitute equation 6 in equation 5. As in also substitute the expression for Fa. Okay. What do we get? Okay, for convenience I am going to call this as 6a and 6b. Okay, I am going to call this as 6b. Now substitute 6a and 6b in equation 5, that is substitute the values of fa and dfa by dt in the expression for dx by dt. Okay, let us write it out. What is it? Dx by dt is fa by c, that is f minus k2x divided by c, plus dfa by dt. What is dfa by dt? That is there in equation 6b, that is df by dt minus k2 dx by dt, the whole thing multiplied by 1 by k1. Is this clear? If it is not clear, you need to go and check the algebra. Please pause the video again and check whether the algebra works out. It is correct, but can you check? You write this in your own notebook and check whether this is correct and whether you are convinced. You need to be convinced. I do think that we have reached our goal. What is our goal? Let us go back and recheck our goal. My goal is to have an expression connecting force rate, deformation rate, K1, K2 and C. Only these I want. I do not want FA, FB, X1, X2. I want F df by dt, X dx by dt, K1, K2, C. This is what I want. Only these things I want, such that I am able to get a relationship between the force applied and the deformation, or the deformation applied and the force. This is what I want. I do not want FA, FB, X1, X2. This is our goal. It seems like we have reached our goal, is it not? Because in this expression I have dx by dt is f minus k2 x by c plus df by dt minus k2 dx by dt times 1 by k1. There is no x1, there is no x2, there is no fa, there is no fb. So, I think I have reached my goal, except that there is some challenge. The challenge is f is present on everywhere, and in particular x is present everywhere. X is present everywhere. Dx by dt is present both on the left hand side and the right hand side. X is present on the right hand side. So, it seems like I have to do a little bit more algebra. I have to collect terms, I have to collect f terms and x terms separately and then write it out. It is better that I do it in this slide itself, so that I can take that to the next slide, otherwise it will be a little confusing. So, let us try to do that. So, collecting f and x terms on two sides of the equation. So, that is what I am doing. I have achieved my goal, but it seems like a very clumsy, confusing equation. So, I am trying to make it a little bit more neat by collecting terms on two different sides of the equation. Okay. So, that means that I am going to do some algebra. So, after some algebra, what I get is the equation 7. This is what I get. Once again, please pause the video and check if the algebra is correct. I have simply rearranged the previous equation such that f and df by dt are on the left hand side of this equation, and x and dx by dt are on the right hand side of the equation. It is simple algebra, but I have skipped some steps, or I have just written the answer. Please check if this is correct. I know that this is correct, but please do check. Okay. Now, it seems like there is some similarity between the Voigt model and Maxwell model with this expression. It seems like there is some familiarity. When I see this, there is some familiarity. What is the familiarity? Well, the second term on the left hand side is absent in Voigt model. is it not? And the first term on the right hand side is absent in the Maxwell model, is it not? So, there is some familiarity. It seems vaguely familiar to the Voigt model and the Maxwell model, but it is not the same. There is some similarity, but it is not the same. Okay. What is absent? The second term on the left hand side is absent in the Voigt model, the first term on the right hand side is absent in the Maxwell model. Okay. That is the similarity. So, for convenience I am going to write out the previous equation in this slide, so that I can continue with the derivation. Okay. So, that is our expression, equation 7 that we got in the previous slide. I have simply rewritten that for convenience. Okay. Now, I would like to factor out K2, factoring out K2 in equation 7. This is why I wrote equation 7, because if I do not have equation 7, I do not know how to factor out K2. So, that will give me, okay. Now, if I factor out K2, this is the expression that I am getting. Now, let me define some time constants tau epsilon and tau sigma. Okay. What these are? Let us see. Define, or let tau epsilon be C divided by K1 and tau sigma be C divided by K2 times 1 plus K2 by K1, or tau sigma is C times 1 by K1 plus 1 by K2. Now, substitute this values of tau epsilon and tau sigma in the expression for force and deformation, or in equation 8. What would I get? I would get F plus tau epsilon dF by dt is equal to, and this is equal to K2 times x plus tau sigma dx by dt. I am going to call that as equation 9. What this means? This means that the force terms relax with time constant tau epsilon, and deformation terms relax with the time constant tau sigma. This is what it means. Okay. Also, I note that this equation is similar to the linear differential equation, the following linear differential equation, which is q plus tau dq by dt is equal to 0 is q. What is the solution? Solution to this equation is q of t is q of 0 times e power minus t by tau. So, for a suddenly applied force or deformation, what is the initial condition? The initial condition is what is the initial condition? That is tau epsilon f of 0 is equal to k2 times tau sigma x of 0. This is the initial condition. Okay. K2 times tau sigma x of 0. Now, let us write out this expression between force and deformation again, so that we can continue the discussion. That is f plus tau epsilon df by dt is equal to k2 times x plus tau sigma dx by dt. This is our equation 9 that we got. This is the expression between forces and deformation that we derived in the previous slide. Okay. And we also said that initial condition is tau epsilon f of 0 is k2 times tau sigma x of 0. Suppose I apply a step change in force. Applied force is some f of t is what? Some f0 times theta of t. I am applying a step change in force. What would be the deformation? That would be x of t is f naught by k2 times 1 minus tau epsilon by tau sigma, the whole thing multiplied by e power minus t by tau sigma, and this whole thing is multiplied by theta of t. So, this will be the deformation when a step change in force is applied. Okay. Now, suppose suppose the applied deformation is some x of t is x naught theta of t. That is, if I am applying a step change in deformation, what happens? That would be f of t is k2 x naught times 1 minus tau sigma by tau epsilon. The whole thing multiplied by e power minus t by tau epsilon, and this whole thing is multiplied by theta of t. Now, that would be the response, that is the force that would be developed when the applied deformation is x of t is x naught theta of t. Or for a step change in deformation, this will be the force that will be developed. From this, I can discuss the creep and stress relaxation responses, is it not? Now, how do I check this? How do I check this? Well, substitute these values of x of t and f of t in equation 9 and it must be satisfied. Equation 9 must be satisfied. I know that it is satisfied, that is why I am writing this down, that is why I am teaching this. But can you take some time and check if this indeed works? Okay, for your conviction and for your understanding, please spend the time and check if substituting x of t and f of t separately in equation 9 satisfies equation 9. It must satisfy, because these are the solutions for these applied force and applied deformations. Remember that. Okay. So, solution means what? The equation must be satisfied. When you substitute the solution, the equation must be satisfied. Check if it is indeed satisfied, that is all. Now, what about creep? When I apply a step change in force, what happens? There is a sudden or immediate increase due to the K1 spring. This is happening due to K1 spring. There is a sudden increase, is it not? There is an abrupt or sudden increase due to K1 spring. Okay. And then the deformation continues to increase as in 1 minus e power minus t by tau, but which tau? Tau sigma, is it not? This is tau sigma. This is increasing as in, this is increasing as in 1 minus e power minus t by tau sigma. Okay. Why is this happening? Due to dash part. And then I am removing this force. When I remove this force, what happens? The strain decays to 0 exponentially, as in e power minus t by tau. Which tau? Again tau sigma. Okay. Why is this happening? Because of the dash part again. Okay. Because of the dash part. So, the immediate response is due to the spring, and the exponential response, whether it is an increasing or a decreasing exponential function, is due to the dash part. Okay. Now, we can immediately see how this response is qualitatively different from the response that we plotted for the Maxwell model. This is qualitatively different from the Maxwell model, is it not? It is a very different response. Why? Because there are many things that we have included that has complicated matters, but has also resulted in this response. Okay. Qualitative difference. Now, what about stress relaxation? Well, when I apply a sudden change in deformation, what happens is that there is an immediate increase in force. Okay. That is expected. There is an immediate increase in force, and then the relaxation happens with some time constant tau. But what is the time constant? That is tau epsilon. In creep I had tau sigma, and in stress relaxation I have tau epsilon. Okay. And this is tau epsilon to some constant value. It decays and then it settles down at some constant value. Once again, this response is different from my expectation from the Voigt model. So, essentially the creep and stress relaxation responses are very different from what I would expect from either just the Maxwell model alone or just the Voigt model alone. Qualitative difference between the Kelvin model and the Maxwell and Voigt models in the creep and stress relaxation. So, that means Kelvin model addresses some of the limitations of the Maxwell and Voigt models, and it incorporates features from both the Maxwell and Voigt model. For example, it avoids the non-physical direct delta function found in one of these responses, is it not? Please check that. Okay. So, in this video we defined another model of viscoelasticity called as the Kelvin model or the standard linear model, and we derived the creep and the stress relaxation function for the same, and we compared it with the creep and stress relaxation functions that we found for the Maxwell model and Voigt model, and we realized why the Kelvin model essentially incorporates the advantages from both the Maxwell model and the Voigt model. Okay. So, with this we come to the end of this lecture. Thank you very much for your attention.